Most people think the internet is a cloud, but if you could strip away the concrete walls of a modern data center, you wouldn't see clouds. You would see a dense, pulsing nervous system of glass. In the last 3 years, we've seen a massive shift. We aren't just connecting buildings anymore. We are building superclusters, where the network is just as critical as the processor itself. In this video, we're going deep into the physical layer, from the Medusa servers with 26 fiber ports to the history of the glass itself, and the timeline of where we're going next. To understand where we are, you have to see the timeline. Fiber tracks its evolution through a language of color-coded jackets. This isn't just about looks. It's about the physics of the glass inside. First, the multipath era. In the 1980s, we had OM1. It had an orange jacket and a thick glass core. Light bounced around inside like a pinball. It was fine for slow speeds, but it's a museum piece now. In the 1990s, we moved to OM2, still orange, still bouncing light, but refined for gigabit speed. Then came 2002, and OM3, the first aqua blue cable. This was laser optimized. It was the standard for the first wave of modern data centers. In 2009, we got OM4, another aqua cable, but higher grade. It allowed for 100 gigabit speeds, but it could only travel a few hundred feet before the signal degraded. In 2016, we saw OM5, the lime green cable. It uses a trick to squeeze 4 shades of light into one strand, but even this is struggling with the newest AI clusters. Now, the single path era. In 2005, the yellow OS2 cable became the gold standard. It has a core so tiny, only 9 microns, that light can only travel in one straight path. Because the light doesn't bounce, it doesn't get blurry over distance. In 2025, these yellow cables are taking over everything. As we hit 800 gigabit speeds, the industry is moving to OS2 even for short hops inside of the server room. How do we reach 800 gigabit speeds? We don't do it with one super fast laser. We do it by bonding multiple lanes of light together in one plug. For years, the industry used the MPO12 connector. It held 12 strands of glass in one plug, but for high-speed data, it usually used 4 strands to send and 4 to receive. That left the middle 4 strands completely empty, and it was a waste of space. Now, we have the MPO16, the AI standard. It puts 16 fibers in a single row. It uses 8 lanes to send and 8 lanes to receive. No waste, 100% efficiency. Think of it like a bridge. Instead of building one car that goes 1,000 miles per hour, we can build an 8-lane bridge. The data is broken into 8 pieces, sent simultaneously, and put back together on the other side. This is why cleanliness matters. One speck of dust on a 16-fiber plug shuts down the entire highway. How do we pack more data into the same strand of glass? For decades, we used binary. The light was either on or off, 1 or 0. But at 800 gigabit speeds, light can't turn on and off fast enough. So the industry switched to PAM4. Think of it like this. Instead of a light switch that is on or off, we have a dimmer switch with 4 levels of brightness. Each pulse of light now carries 2 bits of data instead of 1. This doubles our bandwidth without requiring faster lasers. But there's a catch. Because we are measuring 4 different levels of brightness, the signal is much more fragile. Any noise, any reflection, or any tiny bend in the fiber can ruin the data. This is why AI data centers are so obsessed with signal integrity. They use digital signal processors inside every transceiver to constantly clean up the light as it arrives. And this leads us to the biggest enemy of AI networking, reflectance. When you connect 2 fibers, there is often a tiny air gap. At 10 gigabits, it didn't matter. At 800 gigabits, that gap acts like a mirror. It bounces light back towards the laser, creating noise that drowns out the signal. This is why you'll see techs using APC or angled physical contact connectors. The glass ends are ground at 8-degree angles. When they touch, any reflection is aimed out into the cladding of the fiber instead of bouncing back into the source. But what if you run out of glass? This is where we use bidirectional optics. Usually you need 2 fibers, one to talk and one to listen. But by using different shades of light, we can send and receive on the exact same strand of glass at the same time. This is vital because of the Medusa server. A modern AI server is a cable nightmare. It needs 16 fibers for the processors to talk to each other, 8 to 10 more fibers for storage and the internet, and 2 fibers for management. That is 26 separate glass strands plugging into one single box. And a cluster of 1,000 nodes has 26,000 connections. If we didn't have all these multi-fiber plugs and bidirectional tricks, the machine would overheat from all the cable clutter blocking the airflow. So, the data has left the back of the Medusa server. Where does it go? It starts in the Meet Me room. This is the heart of every data center. When a customer wants to connect to the internet, the data center runs a cross-connect. This is a physical fiber patch running from the customer's rack directly to the provider's rack. It's the most important 50 feet of fiber in the entire world. From there, the data hits the POP, the point of presence. Think of a POP as a digital off-ramp. It's a small facility, often in the middle of a city, where the local fiber networks connect to the massive long-haul backbone. But the ultimate level is the fiber exchange. These are giant, carrier-neutral data centers. These buildings act as the airport hubs of the internet. By connecting in an exchange, data can jump from one network to another in the fraction of a millisecond. This is why AI companies spend millions to be in these specific buildings. Being 1 millisecond closer to the exchange is the difference between a real-time AI response and a loading screen. Once the data leaves the exchange, it eventually hits the ocean. 99% of international data moves through an undersea cable. They are the size of a garden hose, but they are marvels of engineering. Because light dims as it travels, we have to boost it every 40 miles. There are underwater amplifiers at the bottom of the sea, powered by thousands of volts sent through a copper layer inside the cable. Today, the trend is open cable landing stations. Now, the cables plug directly into the big exchanges and data centers we just talked about. This eliminates the middleman, reducing latency and making the global mesh even faster. Sometimes, companies don't just buy a service, they lease the unlit glass. We call this dark fiber. They buy their own lasers and use DWDM, or dense wavelength multiplexing, to turn a single fiber pair into 96 separate channels of light. It's the difference between buying a bus ticket and owning the whole highway. But as we scale these highways, we are hitting a massive energy problem. Moving data over fiber is efficient, moving data over copper is not. Inside a standard server, data moves from the processor to the transceiver over copper traces on a circuit board. As speeds go up, the resistance in that copper generates massive heat. We are now spending nearly 30% of a server's power just moving the data from the chip to the edge of the box. The solution is silicon photonics. We are starting to build the lasers and modulators directly onto the same silicon as the computing chips. Instead of converting electricity to light at the faceplate, the conversion happens inside the processor package. This is the ultimate goal: co-packaged optics. A computer that uses light to talk, not just between buildings, but between cores on the same piece of silicon. When we reach that point, the distinction between the server and the network will finally disappear. While we redesign the chips, we are also redesigning the glass itself. What's next? We are literally trying to beat the speed of light. Light travels 30% slower through glass than it does through air. New hollow core fiber uses an air center to let it zip through at near vacuum speeds. Moving data across a copper circuit board creates too much heat. The future is light, all the way to the silicon. The next time you ask a chatbot a question, remember, it's not just software. It's the millions of miles of yellow OS2 glass and the 16-lane fiber highways making it possible. Fiber is the performance multiplier of the modern age. If you found this deep dive helpful, let me know in the comments. I'm Dan, and I'll see you in the next one.